thank you for this detailed presentation. And considering that we are supposed to keep presentations on schedule, I have 1 hour for this one. First time in my life. I hope I won't use the whole 1 hour, but anyways. So I'm going to talk about strut-and-tie modeling of GFRP-reinforced concrete deep beams. I co-authored this with Shuqing Lu. She's my current PhD student, but this was her work in her master's thesis. So I'm presenting part of her master's thesis. Okay, so first what I'm going to talk about, I'm going to present the problem. There are some problems using strut-and-tie modeling for GFRP-reinforced concrete. I am going to briefly talk about specimens that we use to calibrate our ideas and our model, elements of strut-and-tie modeling, and then elements of analysis. The analysis done using elastic stiffness analysis. Parameters have to be determined for this analysis, and this was the main challenge, I would say, in this modeling. And then we had to decide on the failure criteria, and the overall process of analysis will be presented. It's all in MATLAB or Excel program. And then the results and conclusions. Okay, so first statement is pretty obvious. FRP reinforcements are linear, elastic, and brittle. The fact that a lightweight and non-corrosive is less of an issue with strut-and-tie modeling, but brittle and linear elastic, they do not yield, and you want to have a failure mode governed by concrete crushing. Now, traditional strut-and-tie modeling was developed for steel-reinforced concrete and relied on steel elements yielding at failure, and that made everything relatively simple. Modeling of concrete was important, or is important, because we still model these structures with a strut-and-tie, is important, but not so important, because the failure is governed by yielding of steel. In this case, failure must be governed by crushing of concrete. All of this I actually already said. It's in points here. So we did figure out that statically indeterminate strut-and-tie models. Why statically indeterminate? Because of the flow of stresses, you need a lot of members, so effectively the truss becomes statically indeterminate. Can be used for analysis of these beams if you make certain assumptions. I already said modeling of concrete struts becomes very important. If modeling of concrete struts is important, then also determining the sizes of struts, the sizes of nodes becomes very important when you have GFRP reinforcement in the strut-and-tie model. The first research that we did was done by my former master student, Martin Kral. This was an add-on to his research because he did primarily testing, and he did a quick search whether he could use strut-and-tie to model his own tested beams, and determined that possibly yes, he had some promising results, although not perfect, to be honest, but I don't want to say this. But we took on this work by Martin, and we developed it further, and this is what I'm presenting here. Okay, so these are the tests that we used for our model calibration, our own, Kral and Polak, so they were done at the University of Waterloo. They were semi-deep beams because A/D ratio was 2.5, and we were focusing on stirrups and different stirrup spacings. So this set of beams, there are very few tests like that which do have stirrups and stirrups from GFRP, so that they can be used to calibrate strut-and-tie modeling. Then we used also a set of tests from Kim, which they tested deep beams with A/D of 1.5, 1.7, so much deeper, but they had no stirrups. They were without stirrups. So I'm not going to spend too much time, even though I have the whole hour to describe the test program. This is the experimental setup of our own test, 3-point bending, We had stirrups with different spacings, relatively simple tests. And 6 of our beams are used in this paper for calibration of the strut-and-tie modeling. Now this is the next slide, shows the setup by Kim 4-point bending. That's probably here, you can obviously see. And again, 6 beams from their testing we are using for our calibration. So now coming back to strut-and-tie modeling. Strut-and-tie model consists of what? Nodes, struts, and ties. That's it, right? So the whole topic, the whole presentation will concentrate on determining the sizes of these nodes, sizes of struts, and also constitutive model for struts. Ties, it's linear elastic brittle reinforcement, so in this case, actually pretty simple to model. We have beams without stirrups and we have beams with stirrups. For beams without stirrups, the typical triangular model is used, and what should fail is S2 strut, and this is one load path really, and when this fails, the beam fails. And then there are beams with stirrups. In the case of beams with stirrups, we have such a fan section. The whole section is considered a compression fan. I think if I press the button, oh yeah. And the failure can happen due to different elements failing. Most likely this S11 strut, which is going from all across the whole D region. Sometimes this element fails also, S5. And it will change, the shape of the strut-and-tie model will change with the number of stirrups. If you have more stirrups, it will be slightly different ST model. So now, elastic analysis. We use elastic analysis to solve the problem. Iterative, because the stiffness of the elements change. The stiffness of FRP ties is easy. Constant elastic modulus and constant area, and the stiffness, cross-sectional area times elastic modulus. Well, for struts, we have to use softened concrete compression models. Why softened? Because there is when you have compression in shear region, you have a transverse tension, and depending on how much tension transversely you have, your concrete compression response changes. The question here is how to incorporate this softened concrete, what kind of formulation should be used to model softened concrete response. And the second challenge, which I already mentioned, no, this is actually not yet. Here, cross-sectional area times it's strut width times beam width. So this is, for now, just in this slide, is just the softened concrete models emphasized. Okay, so let's go forward. What did we do? So what does it mean, concrete softened models? It means models which, depending on transverse tensile strain, which I think in this picture would be strain going transversely here, this way, the compression response is going to get softer, or actually less strong concrete in compression. And also the peak, in this case, the peak strain is also moved because of softening. So how did we handle this? First of all, we did literature review. That's what everybody does. So we looked at what kind of softening parameters are used for in different resources. ACI has very simple, with stirrups 0.6375, without stirrups 0.34. There is work done by Neddy et al., and they have to, again, it's a whole set of equations. They have a softening parameters for compression struts in strut-and-tie models. Their tests and their calibration was done on beams without shear reinforcement. So all of them were without shear reinforcement. And then there is Canadian approach based on modified compression field theory, where the softening factor depends on this epsilon 1, which is this tensile strain in transverse direction from compression. In compression goes this way, epsilon 1 is strain in the transverse direction, and according to the code, you can calculate it based on strains in the reinforcements and inclination of compression strut. We actually used all of them. I'm not presenting those results. I didn't know I had the whole hour. So I'm presenting what we chose at the end. But this one, the last one, and all of them, no, this one especially, it relies on this inclination angle. And this inclination angle depends on the number of stirrups. So now it became a little bit of a problem. So we had overestimation of strengths. It's not only predicting of strengths. Strut-and-Tie should be a lower bound model, so we should always be on conservative side. But also predicting incorrect failure mode is a problem. Like you predicted something close, but it predicted something different. And the next thing is predicting different trends. Beams with more stirrups are weaker than beams with less stirrups. It doesn't make sense, and it's not experimentally working this way. So what we proposed is to use modified compression field theory, but because we are programming this whole procedure to calculate epsilon 1 from strains in other directions, different formula, and this epsilon f, I will show this in a second, plus epsilon v is treated as a set. So if we are calculating softening factor for S10, we are going to either use T1 and T6 members and the strains in them to calculate, or T7 and T2, and we'll use the larger one to calculate the softening factor. So this is what we did. And because remember, we have those strains. If the designer doesn't have the strains, the other formula was for design purposes, and you don't have all the strains. But we have a program that calculates the strains in the analysis. Okay, so then we had the problems with beam without stirrups, because how are we going to calculate strains in transverse directions if we don't have stirrups? In the other model, we had stirrups. So here we came up with the idea of imaginary ties. So we did put ties, this is the model that we used, to calculate softening factor for S20. We put ties in the cross section, but they have practically zero stiffness. And we did actually convergence analysis. We chose to use 5 imaginary ties, only for the purpose of calculating the softening factor for S20. And now it's going to all change into green. And I don't know why, but it does. And we did, this is the convergence study. 5 is quite conservative. You can see that as you put more and more of these imaginary ties, the solution converges. So we could use 10, but 5 is conservative, and we thought it's a lower bound solution, so maybe 5. So that's what we did. For calculation, the softening factors. Now, the next problem was calculating the strut width. Strut width is based on the nodes, and I will come back to the nodes as well. So there are, of course, problems. First of problems, there are 2 nodes, one in compression zone, another in tension, if you are loading this direction. Both of them have different width, so 2 values. The solution, you can take average or smaller, which we did, smaller value of the node. And now the next problem, okay, so we know how to calculate the width of the strut, how to calculate the depth of this node. Because using linear strain distribution through the beam member is not valid because it's a deep member, it's a deep beam. So that doesn't work. We tried it, and it didn't produce any good results. Shouldn't have. This slide I won't, this is in the paper, is basically geometry, trigonometry of how to calculate the width of the strut based on the node sizes. So let me skip this because nobody will concentrate on this here. Now, how to calculate the depth of compression block? We did some analysis with finite element analysis. One suggestion which we had was simply to put 0.2D. It was actually working quite well. But the other, a little bit more accurate suggestion was, this is the actual distributions of strains through the depths of the deep beam. This would be the linear approximation, which obviously doesn't work. But the suggestion was to use linear approximation only for the compression part, and then use equilibrium to calculate the depth of compression block. So strain profile is assumed to be linear in compression part only. And then we use Hognestad parabola and internal force equilibrium. I would like to point out here, Hognestad parabola is the model for concrete in compression, very commonly used. We used also other models. This is not so detrimental. You could use other models for any parabola that is describing concrete compressive response. And from equilibrium, we are looking to calculate epsilon top, strain on top of the beam, and the depth C of the compression zone. So we assume that the section is fully cracked. And from this, we can get that the top strain in concrete comes from this formula. Epsilon naught, this is important, this is the strain at the peak of compression. And from this, we can calculate the depth of the compression block. And this part, of course, must be larger than 0, so we limited it to 0. And this will gives you that maximum strain on top is 1.5 epsilon naught, and the maximum value of the depth of this compression zone is 0.833 C. C is the depth of neutral axis. So, okay, that's all. So all of this, of course, is done using the program. It's not done by hand. So we have different failure criteria possible for the strut-and-tie. We have tie rupture, node crashing, strut crashing. Tie rupture we don't like. And node crashing also, if you have node crashing, that means you have done something wrong. So you can increase the bearing plates. What we want is strut crashing. And when is the model becomes, the whole model becomes failed is when enough struts are crashing. And we have, of course, different failures. Shear failure, flexural failure, crashing of horizontal strut, combined failure, crashing of both types of struts, so horizontal and inclined. And both this combined and shear, we called it really shear failure. Sometimes we call it combined, but it really means that the beam failed in shear. Again, this is the whole overall process, and I won't stop here. I won't discuss this in too much detail. And these are the results for remember, we're 6 beams with stirrups, which we tested, and 6 beams without stirrups. So here are the test results. And we have the same, actually the failure modes are consistent with testing. That's not written here, but it is. We also have the same trends. So the beam with less stirrups, spacing of 220, is less strong than the beam with 150. These were slightly different beams altogether, larger cross-section, and they were stronger. And the model predicts exactly the same trend in the results. And this is important. And it is a lower bound. And then for beams without stirrups, with these imaginary stirrups that allowed us to calculate softening factors, we also have test results and predict it, and the trends are the same, similar trends, and lower bound estimation. So it worked for both cases, and these are beams which were not tested by us. And so it's also good that we could confirm this. Okay, so conclusions. The proposed indeterminate strut-and-tie method has the following component. The softened, I wrote here cognizant parabola, but again, softened compressive model for concrete response, the proposed softening factor formulation, and the proposed method to compute the compression block depths. These are the most important parts. And it can be used to analyze shear strengths of FRP-reinforced concrete beams. Hopefully it could be properly formulated so it can be used for design, for beams with and without stirrups. And for future, it would be nice to compare, verify the method with more experimental data. As I said, there's not that much available tests with GFRP stirrups. There are without stirrups, and we have done some more. And also to propose a strut-and-tie method for other D regions, and not just the deep beams, how to use it for design. Okay, and that would be, thank you very much.
Thank you, Mariana, for a very nice presentation and detail. So the floor is open for questions. Yeah?
Okay, Mariana. My question is related to failure modes. Like you presented nicely the theory and the comparison, but you have these extra struts that you have extended to make it an indeterminate truss.
Yeah.
So which one fails first, and what's the sequence until
the main one?
The main one. So once the main one fails, the whole beam.
No. There was one. You have to have enough struts to fail, for the whole beam to fail. But it goes very fast. Once one of them fails, the other will fail at the very small addition of load.
Basically, yours is a lower bound. Once the main one fails, you consider the.
Well, we wait for the program to fail, to crash, but it is very close. Once one of them starts failing, others start failing as well.
Sure. Thank you.
Yeah, will you please come to the
It's okay.
You're good?
Speak loud. So, what is the detail in the end of the bar?
At the end of the bar?
Yeah, how is it anchored? I mean, is it just...
That's an
is there a detail?
Well, okay, so for the testing, if you are asking how it was done, because in our strut-and-tie modeling, of course, we assume that they are fully anchored, right? They are bonded. But in the tests, I did the test, the first set of tests was our test. They had very long development lengths. We are not showing this. These beams were A over D 2.5, but in reality, they were huge. They were very long because we wanted to have proper development lengths past the support. But, remember, these were test specimens. In the continuous structures, you might have enough space to develop the bars. But in a test, well, in a simply supported structure, you just have a beam, right? So how do you develop FRP bar past the support? Well, you just build an overhanging portion that is actually long enough to anchor the bar. We didn't have any slip of the bars during testing. No. We provided enough development lengths for each of the bars past the supports. I didn't show the full picture of the beams during testing, but they were anchored.
So in your node region, in the lower node region, which is exactly above the support of your truss,
Yeah.
your strut-and-tie, at that point, the bar is assumed to be developing its
Yes.
strength.
Yeah.
So that means that the node just extends over the support length, but there is an extending
Yeah.
beyond.
Yeah. That's what we did in tests, yes. Yes, to make sure that we have fully developed bars. In the region that we were testing, the bars were fully developed. And which was the simply point.
I have another question. There's no need to go. For finding the nonlinear strain distribution across the depth of the beams, you showed my element determination and it was nonlinear as expected. And then it was good that you connected the neutral axis point with the extreme strain point. But you don't know these two variables, and you said that you're going to use force equilibrium.
Yeah, we did that. We used force equilibrium. We assumed the section is fully cracked. We did quite a lot of approximations. Yeah, I can go back to this if you. Yeah, I would be happy to do. Oh, time! We have 1 hour. Yeah, we did that. There are quite a few assumptions there. No, this. No. Oh, this whole thing, right? And then if you go back, so this is this is the triangular strain distribution in the compression zone, and then you calculate epsilon top and C, and the depth of the compression block, so the resultant of this. Yeah, and you have equilibrium. So you have equilibrium of forces, and then you have to assume that it's fully cracked, which is an assumption. So you have another equation, and from this you can actually calculate epsilon top with some. And then we also made this assumption that this one cannot be less than 0, because sometimes it actually ends up being 0. So it cannot be less than 0, so it's limited to 0. And this gives you these two equations.
These are the maximum values.
Maximum, not the max. No, this is the maximum what we are allowing. So yeah, so there are some assumptions of it, and also this distribution in compression zone is also not perfectly linear. We have in our full research we are comparing this whole process with just assuming that it's 0.2D. And that's much simpler, and it also works. So you could use 0.2D for design, but I think a little more studies should be done to verify that. Okay.
Any other question, comments? Maybe I ask a question, if you don't mind. So probably I missed that part. I went to finish my sandwich without making a noise. Co-chairing conference, lack of time. Just to be clear to myself, or maybe some people might be interested in conceptually different between steel-reinforced concrete beams and FRP-reinforced concrete beam with respect to the strut-and-tie model. What's the main difference, and what?
I think the main difference is that with the steel strut-and-tie, you're basically modeling flow of stresses through the member, and with steel you want reinforcement to yield before concrete crashes. So if your model for concrete is not perfect, as nodes sizes are not perfect, you basically just have to ensure with your design that those elements do not fail first. That's all you need to do. Your reinforcement is yielding first. Here it's completely different. You don't want your reinforcement to break. You have to model concrete in compression. And therefore the size of the node in the compression zone becomes so important, because based on the size, the failure value changes. Everything changes, right? So
now it's clear to me.
So this is the.
So then I have to go back a little bit to your formula there, because you're assuming that C, the concrete has already crashed. The section is already cracked.
Cracked, not crushed. Yeah.
Do you don't have any assumption when it is not yet cracked.
No, it become all equations become more complicated. We try to make it simple, so we assume it's fully cracked. Also, fully cracked would be an extreme case, and it's a lower bound solution. So you just want to be, predict lower strengths than was in the test. Lower strengths, proper failure mode, and consistent with logic. Like more stirrups will give you slightly more strengths. Even if not much, there should be more. Yeah, so. But all these strengths depends on the softening factors. So if your softening factors are not logical with the, let's say, spacing of stirrups, then you will suddenly have completely different results from modeling. So.
I have a follow-up question. I'm not sure if you might have answered or not. So regarding the new ACI 440 code, I was wondering if you could update us. What is in the code right now?
I think there's nothing.
There's nothing.
Nothing. The Canadian code has something, but it's very, very little.
Okay.
And in ACI, nothing. Which I think is right, to be honest, because if you don't know something, you don't put it in the code. Yeah? You wait until you know. You have some concept.
So I assume Doug is here. It's in the pipeline, yeah, correct?
It's something that we want, but yeah, right now it says does not cover.
Doesn't cover, no, nothing.
Chapter 23 is a very empty chapter, but
Yeah.
not impressed yet.
But maybe there will be something.
We'll be talking about it.
We will be talking.
So I guess this research is well justified. There is a real gap and it needs to be filled. Okay, any follow-up question, comment? So thank you, Mariana.
Thank you very much.